Ladies and gentlemen, welcome to the Island of the Mole. Okay, so we spent an entire unit on dimensional analysis and mole conversions. What we were doing during mole conversions is, if you remember, grams to moles to particles. And we went in all directions, started in different places, and we just kind of ran that into the ground. Now we're going to take that a little bit further. So if you look right here, this is what we call Mole Island. So Mole Island is actually a collection of separate islands. And to get from one island to another, you got it, dimensional analysis. And so, for example, if we start here on Mass Island, we can get to Mole Island by doing a little bit of dimensional analysis. From there, we have our choice of 3 different islands we can go to. And we can go from one island to another only by jumping from one to the next. So if you look closely at our little Mole Island diagram, you're going to see right here where we go from mass to moles to particles. So that little subsection right there, that little trip, would be this guy right here. So before, when we were doing mole conversions, we were just looking at a small section of Mole Island here. We're going to expand it now to a much larger region. And just like when we did these conversions right here, you could only go from grams to moles to particles. You couldn't go directly from particles to grams. You have to go in a step fashion. So what this shows us is the islands that you can jump to get from one to the next. And so there is no connection directly from mass to particles. So you have to go mass to moles to particles. The new journey that we're going to be making, it starts at mass as well, goes to moles, but then it goes to another mole, and then over to mass. And so this little stretch right here is where we're going to start out. Volume and particles are going to be something we'll look at later. And so what we can see here is if we want to look at the mass of one substance and go to the mass of another substance, we'd have to go from grams to moles to grams. And all of these journeys through Stoichiometry Island involve a chemical reaction. So when you look at a chemical reaction, you use it in order to make these conversions. Before, we were given things just like, you've got 1.34 grams of zinc, how many moles is that, or how many particles is that? So we didn't have a chemical reaction involved at all, just a single element or compound. Now we're going to be looking at chemical reactions and using them to make this journey. So here's the diagram expanded and expounded upon. So keep in mind as you're looking at this, the journey that we're making for right now is just this one right here. So if you're copying this down, which you probably should, you just need to copy down this section right here. And what it shows is in order to get from mass of our known substance, so our given, you would have to first convert that from grams to moles. And we do that with the molar mass from the periodic table, just like we did before. The new step is going to be from moles to moles. And so this would be moles of our known to our unknown. So in a chemical reaction, this might be the reactant and that a product, or it might be the amount of one reactant and the amount of another reactant. And so to go from mole to mole, you would use the coefficients, that's the large numbers, in a balanced chemical reaction. And so we go from grams to moles to moles, and then from moles to grams. And to get from moles of our unknown into grams of our unknown, again, we just use our periodic table mass. So let's zoom out real quick so you can see what I mean. Let's take an example problem of, we'll do propanol burning. So here's our balanced chemical reaction, and we're going to need this in order to make this complete journey. So let's start off simple. Let's say we have 3 moles, so 3.0 moles of C3H8O. So from 3 moles of propanol, C3H8O, how many moles of, let's say, carbon dioxide can we make? So in order to make this conversion, right off the bat, let's make an X and a line, because it's dimensional analysis, and that's what we always do. So what unit's going to go on the bottom of that line? Yeah, it's got to be moles of C3H8O. Why? Because that's what's on top. And so if we kind of go over here to our mole island diagram, we are looking right now at moles, and the mole island that we're on right now, because there is 2 choices, is the moles of our known, because our known is C3H8O, and we know that we have 3 moles of it. Our unknown, what we're looking for, is the moles of carbon dioxide. And so from moles of known, we can hop right to the moles of our unknown. And the moles of our unknown would mean that on top goes moles of CO2. Why does that go on top? Because that's the next island in our journey. Now we can throw some numbers on this equation. So we look at our reaction right up here, just as specified. So we use the coefficients from the balanced chemical equation. That would be these large numbers. So looking at the chemical reaction, we would see that there is 2 propanols for every 6 carbon dioxides. That means it's a 2 to 6 ratio. And so that means there's 6 moles of carbon dioxide for every 2 moles of propanol. And so what we can see from this then is these large numbers that we've been balancing with are actually really important because they help us with the stoichiometry. And what they show is the number of moles of each of that substance in the reaction. And so we've got 2 moles of propanol, 9 moles of oxygen, 6 moles of carbon dioxide, and 8 moles of water. That means we would need 2 moles of that and 9 moles of that as our ingredients. So that's what we need in order to make 6 moles of carbon dioxide and 8 moles of water. But anyway, let's go back to our problem. Moles of propanol cancels out moles of propanol. We're left with moles of carbon dioxide, and that's what we wanted to find anyway. So we can go ahead and solve this, and we would see that we would produce 9 moles of CO2. Something I want you guys to notice here, when I'm writing this out, notice how I write out the entire thing. So 3 moles of C3H8O. Back when we were doing just regular mole conversions, the molecules never changed, and so we just wrote things like 3 moles there and 6 moles there and then moles in our answer. We need to write the substance as well, so the molecule as well. The reason for that is because we start with C3H8O, but we end with CO2. And if you're not writing those molecules down, it's real easy to lose track along the way. All right, let's challenge ourselves. Let's say instead of starting with 3 moles of propanol, we're going to start with 4.5 grams of propanol. So if we have 4.5 grams of propanol, how many grams of carbon dioxide will we produce? So that's our known, that's our given. What's the first thing we're going to do? We're going to draw an X and we're going to draw a line. Why do we do that? Because it's dimensional analysis. And not even thinking, we're going to put grams of C3H8O on the bottom. Why? Because that's what's on top before. So what this means is we are on the known side of mole island, and we are right here with mass. We're with mass because it's grams, so we're starting right there. What's the only island we can go to from mass of known? The only island is moles of known. And so what does that mean for our dimensional analysis? It means moles of C3H8O are going to go on top. And what do we use to make that conversion to get from grams to moles of a particular substance? Well, since we're dealing with C3H8O right there and right there, so we're not changing the molecule, we're still unknown, we're going to use the molar mass. And so this is the old familiar task of just doing the 60.0 grams, that's how much propanol weighs, over, and then 1 mole on top. Notice how on this step right here, I didn't use the 2 that's up there. That's because 60 grams of propanol is 1 mole of propanol. So 1 mole of propanol weighs 60 grams. If I put that 2 right there, I'd have to put 120 down there because 2 moles would weigh double that amount. In short, and a really important note to your future self, the only time you use these balancing coefficients is for this little trip right here. You never use those balancing coefficients anywhere else. And so grams of propanol cancels out grams of propanol. We are left with moles of propanol, which means we're right here on our moles of known. So then we can go with our next step. So X line, what's going to go on the bottom of that line? What do you know? Moles of C3H8O, because that's what's on top. After our moles of known comes the moles of unknown. And so our unknown in this case is once again carbon dioxide. And since it's a mole island of our unknown, it's going to be moles of carbon dioxide. Now for this step, once again, we look at balancing coefficients. It's a 2 to 6 ratio still. And so we'd put a 6 there and a 2 there. Moles of propanol cancels out moles of propanol. And we are now on mole of unknown island. Let's go all the way to mass. Let's figure out how many grams of carbon dioxide we're going to make. Looks like I'm going to run out of room, so I'm going to move this down. So X in line, what's going to go on the bottom of that line? Oh yeah, moles of CO2. And on top, the next island in our journey, mass of unknown, which means grams of CO2. That conversion again, we do not use the coefficient from the reaction, so it's not 6 moles of CO2 anymore. We're back down to just 1 because we're looking at the periodic table mass, which is 44.0 grams for every 1 mole. Moles cancels out moles, and we are ready to solve this. Solving this one, be careful with it, so go ahead and type this in your calculator. Just make sure you get the same thing I do. So a good calculator typing would look like this. You need everything that's on top, so 4.5 times 6 times 44, all in parentheses, so your calculator does those together. And then you divide that by 60 times 2. That's what's on the bottom. So you need to make sure you use parentheses. If you left the parentheses out on either one of these, you're going to get the wrong answer. Guaranteed. And so when we do that, what you should show up with is 9.9 grams of CO2. All right, following this video, you're going to see 3 more videos called practice problem videos. What those videos go over are these 3 questions right here. You're welcome to watch as many or as few of those as you want. So I want you to try these problems in your notebook if you can. And if you think you get them right, go ahead and just watch to the end of those videos, check your answers. If you're good, you're good. If you're struggling a little bit, maybe you need a little bit more help, go ahead and watch the videos one at a time until you feel comfortable with this information. And if you're copying them down, this is just a screw up. That should be an arrow right there showing a reaction. Let's look at the wording of these questions real quick. What you're going to see in each question is the word excess. And so each one, this one has excess oxygen, excess chlorine, and plenty of lead sulfate. What that means is we don't have something that's going to stop the reaction or something that's going to run out first. And so if we think back to our peanut butter and banana sandwiches, if you have 2 slices of bread, you have to assume that you have plenty of bananas and plenty of peanut butter in order to make the sandwiches from the 2 slices of bread. So that's what it's talking about. It just means that you're not going to run out of your other ingredients. You're just going to run out of the given. So good luck. Please come to class prepared with specific questions. This is going to be challenging at first. It's going to look difficult, but it's not that hard once we get plenty of practice in, I promise you. So just stick with me. We'll get through this. We'll have a lot of fun doing it.